All right, the final question or final problem from the test to help you out on test corrections. Number 19, a 5 kilogram ball moving at 8 meters per second strikes a stationary 85 kilogram man on the chest, after which the ball bounces back at 2 meters per second. So we've got this poor, unlucky guy standing here. A ball comes in. Oh, that ball's as big as his head. Hits him and then bounces back. This is a full-on elastic collision. So there's going to be some transfer of the momentum, but it has to remain the same throughout the whole process. So our initial, I'm not going to get the whole format here for the conservation graph. We've got the ball at 5 kilograms moving at 8 meters per second. That would scale us out to a positive 40 momentum value there, kilograms times meters per second. We've also got initially the guy standing there with 0 velocity, so he wouldn't contribute anything to the momentum initially. Final, over here, the ball bounces off the way it came. If you remember previous problems, that means we're going to have a change in the sign. It bounces off the way that it came at 2 meters per second. -2. Goes back the way it came. If it's coming towards you, it's positive. If it's going away from you, it's negative. You could flip it around if you wanted to. You'd still get the same answer, but it's just a little bit more weird, confusing. So we've got a little bit of negative momentum over here, and the guy, now he's moving. He just got whacked by this giant ball. But he's got some velocity. If we look at it this way and kind of compare, we got 40 here, we got -10 here. It still has to remain the same, so we're going to have some positive momentum in that direction. You didn't have to draw that in. I accepted it without that part of the graph being drawn in. If your graph looked like you had no idea what you were doing, you lost some points. The momentum conservation equation, again, for an elastic collision, this would be m1 v1 plus 0. This 0 is from our guy right there. He's not moving, so he has 0 momentum. I did accept if you wrote just m2 v2, I would assume that when you put the 0 in there, you'd get 0. Equals m1 v1 plus m2 v2. Everything's moving afterwards. The ball is moving, our mass 1. The man is moving at some unknown velocity. So the last part of the problem, if the man who is wearing high quality rollerblades, quality matters with your rollerblades. Does anyone wear rollerblades anymore? Anyway, if the man was originally at rest, what is his final velocity? So we're trying to figure out the final velocity of the man, which is that value right there. We know everything else, so we just plug and chug. m1 v1, that's 5 times 8. Plus 0, I'm not going to write that down, equals m1 v1 after, so that's 5 times -2, that's -10, plus 85 times v2. Solve this out algebraically. 5 times 8 is 40. I'm going to add 10 to both sides, so I'll have 50 divided by 85 equals v2. Flip this around and solve for v2 because we don't like unsolved fractions. 50 divided by 85, that's much less than 1. It's actually 0.59 meters per second. Remember, the biggest mess up I saw with people was right there. You forgot that if it goes away from the person, it's going to be negative. You have to indicate the direction of your velocity. Velocity is a vector. It has speed plus a direction. Make sure you indicate what's going on with that. Otherwise, your problems are going to be wrong, as some of you unfortunately found out. Those are the problems. If you have other questions on the other ones, drop me an email or let me know in class.